Power. In this lesson, we're talking about what power is, watts, electricity generation, vehicle power, and horsepower. Power. Power is the rate of doing work or transforming energy. It's a scalar quantity, keeping in mind the unit for energy is the joule, and since we're discussing a rate, it must be over a time period. That's what a rate is. It's something over a time period. And power, therefore, is joules per second. Energy used per second. And the unit is the watts. The formula is going to be E over T, and since change in E, like we discussed prior, is equal to the net work, we can also say that power is equal to net work divided by time. Watts. Watts and kilowatts are commonly used to indicate the power of electrical appliances. This tells us how much power they consume per second of operation. So for instance, a light bulb is 11 watts. It's going to use 11 joules of energy per second of use. A hairdryer, on the other hand, is going to use 1500 watts. So 1500 joules per second. So a significant increase. One thing you might notice as we go through this chart is that when we use heat equals an increase in power usage, in energy use per time. So the more heat, the more energy is needed per second of use. Watts. Megawatts and gigawatts are often used to rate the power of electric generating stations. This rating indicates how much energy the station generates per second. So for example, the Ratcliffe coal-fired power station in the UK has a rated capacity of 2 gigawatts or 2000 megawatts. So it's going to produce 2 gigawatts of electricity. In other words, 2 gigajoules of energy per second. Check your understanding. A 51 kilogram student climbs 3 meters up a ladder in 4.7 seconds. Calculate the student's gravitational potential energy at the top of the climb and power for the climb. So for A, we need to find the gravitational potential energy. So Eg equals mgh. We know the mass is 51 kilograms, g is 9.8, and the h is 3 meters. So that equals to 1499.4 joules. We need 2 sig digs in our answer, so our answer becomes 1.5 times 10 to the 3 joules. B, what is the power for the climb? Power is going to equal to change in energy divided by time. The change in energy in this case is the Eg, so we're going to use 1499.4 divided by 4.7 seconds, and we get 319.02 watts. 2 sig digs becomes 3.2 times 10 to the 2 watts. Check your understanding. An 85 kilogram man climbs from a height of 2,900 meters to 3,640 meters in 60 minutes. What is the man's average power? So we need to find out the Eg, right? Similar to the question we just did, we're not given quite as much information. Eg is going to equal to mg, and then change in height. The mass is 85, the g is 9.8, and the change in height is 3640 minus 2900. And that equals to 616,420 joules. But we're looking for the power. Power is going to equal to change in E over change in time, and the time needs to be in seconds. So 616,420 joules divided by 60 minutes. And there's 60 seconds per minute. So minutes cross off, and we get an answer of 171.2 watts. We need 2 sig digs in our answer, so our final answer becomes 1.7 times 10 to the 2 watts. Check your understanding. The power rating of the world's largest wind generator is 3 megawatts. How long would it take such a generator to produce 1 times 10 to the 12 joules, the amount of energy needed to launch a rocket? And we need our answer in days. So our power is 3 megawatts. That's 3 million watts. Time is our question, and our E is 1.0 times 10 to the 12 joules. P equals E over T. T is going to equal to E over P. 1.0 times 10 to the 12 divided by 3 times 10 to the 6 equals 3.3 times 10 to the 5 seconds. So 3.3 times 10 to the 5 times 1 minute per 60 seconds times 1 hour per 60 minutes times 1 day for 24 hours. So you see our hours get crossed out, our minutes get crossed out, our seconds get crossed out, and we're left with an answer of 3.9 days. The nuclear generating station located in Pickering, Ontario is rated at 2,160 megawatts. 2160 megawatts. How much electrical energy in megajoules can the station produce in one day? Well, P is going to equal to E over T. We're looking for E. E is going to equal to P times T. Power is 2160. Now we're going from mega to mega, so we can just leave it as is. So 2160 megajoules times the time in 1 day. So you have 60 seconds in 1 minute times 60 minutes in 1 hour times 24 hours in 1 day. And that gives us an energy output of 1.87 times 10 to the 8 megajoules per day. The Lamborghini Murcielago LP 760-4 Super Veloce has a weight of 3,450 pounds and can go from 0 to 60 miles per hour in 2.8 seconds. What is the average power output of the car's engine in kilowatts? So there's a bunch of conversions that we need to do to answer this question. So first of all, the mass is 3450 lbs pounds, and there is 1 kilogram per 2.2 lbs. So to figure out the mass in kilograms, we take 3450 and divide it by 2.2, and we get 1568.2 kilograms. And it can go from 0 to 60 miles per hour in 2.8 seconds. So time is 2.8 seconds. What is the average power output of the car's engine in kilowatts? Power is going to be equal to energy divided by time. So now what's the energy that we have in this case? Well, that's going to be EK. Now EK is going to be 1/2 mv squared divided by time. So now we know most of the things, right? But we do not know the V. V is the question. We know it goes from 0 to 60 miles per hour, and we know that 1 mile per hour is going to equal to 1.6 kilometer per hour. So if we take 60 times 1.6, we find out that it goes from 0 to 96 kilometers per hour in 2.8 seconds. Now we're not quite done yet, because we need 96 kilometers per hour in meters per second. So we're going to multiply. We're going to say 1 kilometer is equal to 1,000 meters. And we know that 1 hour is 3,600 seconds. So that gives us an answer of 96 times 1,000 divided by 3,600. So 26.7 meters per second. So now we can answer our question. So the power is going to be the change in EK, which is going to equal to 1/2 the mass, which is 1568.2, times 26.7 squared divided by 2.8 seconds, which is equal to 2.0 times 10 to the 5 watts. The question asks for it in kilowatts, so it's 2.0 times 10 to the 2 kilowatts. So that's the power output of this vehicle, 2.0 times 10 to the 2 kilowatts. Now, similar question. The Tesla 3 Performance has a weight of 1800 kilograms and can go from 0 to 60 miles per hour. So we know our velocity is still going to be the same at 26.7 meters per second. And the time is 3.2 seconds. What is the average power output of the car's engine in kilowatts, and how does it compare to the previous question? So P equals change in E divided by T. Change in E is still going to be EK, so that's going to be 1/2 1800 times 26.7 squared divided by 3.2. And that gives us a power output of 2.0 times 10 to the 5 watts, which is equal to 2.0 times 10 to the 2 kilowatts. Exactly the same as the Lamborghini. Horsepower. Horsepower is a unit of measurement for power. It's one you've probably heard of, but don't really know what it is. 1 watt is equal to 0.00134 horsepower. 1 kilowatt is therefore equal to 1.34 horsepower. So looking at the previous question, what is the car's horsepower? Well, power is going to equal to 201.05 kilowatts. That was the unrounded number. We're going to multiply that by 1.34 horsepower per kilowatt, giving us a horsepower of 269 horsepower. So both the Tesla and the Lamborghini have a horsepower of approximately 269. So as an aside, when the steam engines began to do work with horses in the mines in the early 1800s, the mine owners wanted to know how many horses these engines would replace. So James Watt, the person who invented the steam engines, figured out a mathematical way to equate the number of horses to the engine power, and that's where we got horsepower from. And it's still used today. A lot of boat motors use horsepower as the only way of describing the power output of the motor. And that concludes our lesson on power.